Have you ever wondered what powers the most advanced spacecraft, or how we might one day travel to distant planets in the solar system? Picture this: a spacecraft gliding silently through the cosmos, fueled not by conventional means, but by the incredible energy of the atom. Today, we're diving into the fascinating world of nuclear-powered engines. Buckle up, because this is going to be an exciting journey into the heart of atomic propulsion. To understand how a nuclear-powered engine works, we first need to grasp the basics of nuclear energy. At its core, nuclear energy comes from the process of nuclear fission, where the nucleus of an atom is split into two or more smaller nuclei, releasing a tremendous amount of energy in the process. This energy can be harnessed for various purposes, including generating electricity and, of course, propelling spacecraft. Now, let's break down the two primary types of nuclear propulsion systems: nuclear thermal propulsion and nuclear electric propulsion. Each operates on different principles and has unique advantages. Let's start with nuclear thermal propulsion. In this system, a nuclear reactor heats a propellant, usually hydrogen, to extremely high temperatures. Imagine a kettle boiling water, but instead of steam, you're producing a superheated gas. This hot gas is then expelled through a nozzle, creating thrust that propels the spacecraft forward. The beauty of nuclear thermal propulsion lies in its efficiency. Traditional chemical rockets burn fuel to produce thrust, but they have limits on how much energy they can produce. In contrast, a nuclear thermal engine can generate much higher temperatures, resulting in a greater specific impulse. Specific impulse is a measure of how effectively a rocket uses propellant. Higher specific impulse means the spacecraft can travel further with less fuel, making it ideal for long missions, like those to Mars or beyond. So, how does a nuclear thermal engine actually work? Let's break it down. The heart of the system is the reactor core, where the fission reaction occurs. Inside the core, fuel rods made from enriched uranium or plutonium are arranged to maximize the fission process. When a neutron collides with the nucleus of a uranium atom, it splits, releasing more neutrons that continue the chain reaction. While this reaction generates a lot of heat, it also produces radiation, which must be carefully contained to protect the spacecraft and its crew. This is where shielding comes into play. Thick layers of materials, often including hydrogen-rich substances, encase the reactor to absorb radiation and keep everything safe. Once the fuel is sufficiently heated, it is pumped into a combustion chamber where it mixes with the propellant, usually liquid hydrogen. This mixture is ignited, producing a high-pressure, high-temperature gas. The gas then expands and is expelled through a nozzle, creating thrust. This process might sound complicated, but at its core, it's a powerful way to utilize the energy released from nuclear fission. Now let's shift gears to nuclear electric propulsion. Unlike nuclear thermal systems, nuclear electric propulsion generates electricity using a nuclear reactor, which then powers electric thrusters, like ion or Hall effect thrusters. This method is quite different from traditional propulsion systems that rely on combustion. In a nuclear electric system, the reactor generates heat, which is used to produce steam that drives turbines connected to generators. This process converts thermal energy into electrical energy. The electricity produced can then power various systems on board the spacecraft, including the electric thrusters. Electric thrusters work by using electric fields to accelerate ions, which are charged particles. These ions are expelled at incredibly high speeds, producing thrust. Although the thrust produced by electric engines is much lower than that of chemical or thermal engines, they are highly efficient and can operate for extended periods. This makes them particularly suitable for deep space missions, where long durations of constant thrust can lead to significant increases in velocity. One of the most notable advantages of nuclear electric propulsion is its ability to operate continuously. While chemical rockets provide a powerful but brief burst of thrust, electric thrusters can run for days, weeks, or even months, gradually increasing the spacecraft's speed. This characteristic is particularly beneficial for missions that require extensive travel across the solar system, such as crewed missions to Mars or asteroid belt exploration. Now let's talk about the challenges associated with nuclear-powered engines. Safety is paramount. The idea of launching a nuclear reactor into space might sound alarming, and rightly so. Engineers and scientists must ensure that these reactors are safe, reliable, and capable of withstanding the harsh conditions of space travel. This includes rigorous testing to prevent any potential accidents during launch or in space. Furthermore, there's the issue of political and public perception. The use of nuclear technology in space is often met with skepticism due to historical accidents and the potential for radiation exposure. Gaining public support and regulatory approval for such projects can be a significant hurdle. Despite these challenges, the potential benefits of nuclear propulsion are immense. As we look to the future of space exploration, nuclear-powered engines could play a crucial role in overcoming the limitations of current propulsion technologies. Imagine missions that last for years instead of months, or crewed journeys to distant planets that become feasible with the efficiency of nuclear energy. In fact, several space agencies are already exploring nuclear propulsion technologies. NASA has been conducting research on nuclear thermal propulsion for years, and they're planning missions to test these systems in the near future. The European Space Agency is also investigating the use of nuclear electric propulsion for deep space missions. Another exciting aspect is the potential for hybrid systems that combine nuclear propulsion with other technologies. For instance, researchers are looking into combining solar power with nuclear engines to create a more versatile propulsion system that could adapt to various mission profiles. In conclusion, the world of nuclear-powered engines is both complex and promising. By harnessing the power of the atom, we could redefine what's possible in space travel. Nuclear thermal propulsion offers high efficiency for long-distance missions, while nuclear electric propulsion provides the ability to operate continuously over extended periods. Though challenges remain, the potential for these technologies to revolutionize space exploration is undeniable. As we continue to push the boundaries of our understanding of the universe, nuclear propulsion may very well be the key to unlocking the mysteries of distant worlds and beyond. So the next time you gaze at the stars, remember that the future of space travel could be powered by the very atoms that make up our universe.